Welcome to today's webinar, Airborne Earth Observation, a critical pillar in Earth observation sciences and applications. Welcome to our three speakers and to our participants, of whom there's a good number. I'm Megan Lewis, Acting President of Earth Observation Australia. This webinar is the fourth in a series leading up to the Advancing Earth Observation Forum that'll be held in Brisbane, 22nd to the 26th of August this year, 2022. So the webinars aim to engage you in some hot topics in Earth observation, build connections in our Earth observation community, and start conversations in advance of the forum. In opening the webinar, I acknowledge the traditional owners of the lands and waters of all of Australia, the country on which we live and which is the focus for so much of our work. I offer my respect to elders past, present and emerging, and aim to build our shared knowledge and experiences. I'd also like to remind participants of the Earth Observation Australia Code of Conduct for this event. You can find that on our webpage. Simply, please be professional, considerate and respectful to others, and open to discussing a diversity of ideas and perspectives. Just some housekeeping matters. Please note that the session is being recorded, and because of the large number of participants, please keep your webcam off. But during the whole session, please post any comments, perhaps to particular speakers or more general comments and questions in the Zoom chat. And we'll be keeping an eye on those, and we're having a question and answer session after the three presentations. So airborne sensing, our topic. Airborne sensing's had a long history, predating satellite Earth observation. And as an academic, I confess I've quite often talked about airborne sensing right at the beginning of Earth observation lectures or courses. Airborne sensing continues to provide unique capabilities and play numerous unique and distinctive roles in Earth observation. So in this webinar, we're hoping to demonstrate some of the capability and extent of the airborne EO industry in Australia and identify directions for collaboration between the airborne sector and space and ground-based Earth observation activities. And so to do that, we have three very highly qualified speakers with extensive experience and backgrounds in airborne sensing. Andrew McGrath, Paul Dare, and Andrew Krummel. So they're each working in different subsectors or different aspects of airborne sensing. And so this is an opportunity to discuss different planned and current activities across industry, research, not-for-profits and government sectors. So rather than launch into my introductory lecture, as an opener to our webinar, we've posed a somewhat provocative question to our panelists, and we're going to ask them to just give a brief response. So as an icebreaker to our three panelists, given the current national focus on satellite-based Earth observation, what future roles do you see for airborne sensing, your particular expertise and domains? Short answers. We'll introduce each of the speakers more fully when they do their whole presentation. So Andrew, perhaps if you'd like to give us a quick thought on that.
Oh, well, as an icebreaker, before my presentation, which does look at this, I mean, it seems obvious that there's a resolution. Resolution, you know, if you want to measure something in fine detail, being close to it is a really big help. You can see it better. You can choose when you're going to do it as not with a schedule that's not dictated by orbits. you can change things and you can customize things, whereas your satellite is sort of fixed in. Once it's up, it's hard to change. And there is also a big area for airborne measurements in support of satellite observations, both in terms of engineering development as well as calibration and validation and that sort of thing. So I guess that's my shortish answer.
Thanks very much, Andrew. Paul, your thoughts?
Yeah, good day, Megan. An interesting, and yeah, you're right, very provocative question there. I think it's a topical question. It's one I get asked a lot of the time. I'm talking today from the perspective of a owner of a tech company. I often find myself talking to investors, and investors always ask me the same question: why are you using airborne sensors? Why don't you use satellites? There seems to be something terribly old-fashioned to people not in our industry, something terribly old-fashioned about using manned aircraft for remote sensing. Satellites sound so much more interesting, and when those investors are talking to their stakeholders, that they need to sell the idea, and selling the idea of satellites is so much easier than selling the idea of using sort of old-fashioned aircraft for remote sensing. Just I suppose to repeat what Andrew said, yeah, simple fact is for the work we do, for the projects that we get involved with, you simply can't use satellites. We might need a sensor over a particular area. Geostationary satellites don't have the resolution, and low Earth observation, low Earth orbit satellites don't have the loiter capability. And I think another aspect is that end users of remote sensing data are becoming a little bit more picky. They're starting to understand what data actually involves, and they're starting to pick the actual time and date and resolution and spectral bands of the data they want, and very often satellites are too constraining. But even though airborne remote sensing has a lot of benefits, I think we're still going to see the national focus, as you mentioned in your question, will be on satellite-based systems, because that's much more exciting.
Thanks very much, Paul. And I think I can imagine your presentation is going to pick up on some of those points as well. Daniel, your thoughts about this?
Yeah, look, I think, probably echoing some of the previous comments, that I would see a lot of this technology as supplementary rather than, one or the other. Each one has a time and a place and a benefit. Particularly, I come definitely more from the commercial side as a company that flies around quite a number of airborne sensors. Some of the things that we're seeing, and I'll touch on this a little bit more, from a value perspective, I think the business models around satellite imagery for those smaller localized areas, sometimes don't stack up. When we can still deliver it at a cheaper and better value. I shouldn't say cheaper, but a better value proposition than what can come from a satellite. So I think that maybe there's some business model aspects there. But look, probably a little bit contradictory to what Paul just said. We're also sort of starting to see that whether we're getting the imagery or the solution for our clients from a satellite or from a manned aircraft or from a remotely piloted aircraft, some of our end users are really just focusing on the answer. A little bit less concerned about the platform, as long as we can guarantee them that, hey, for your monthly stockpile volumes, for example, we're giving you the right answer. They're probably, and we're signing away on the accuracy in what we're giving. They're probably not as fussed by the end technology, but that's probably different users to what Paul's dealing with. So that's the long-winded answer. The short-winded answer is I think airborne observation, still has a very, very bright future, but I'll touch a little bit more on that in time to come.
Excellent. Thanks very much, Daniel. And I'm sure the audience is reacting to some of the comments that people have made so far. So please post your thoughts as comments in the chat window, and we'll pick them up later. So now, after that opener, we'll move on to presentations from our three speakers. And First of all, I'd like to introduce Dr. Andrew McGrath, our first speaker. Andrew's worked at Airborne Research Australia since 2009, and he's been a director there since 2017. And at ARA, he leads a range of environmental, airborne, sensing and analysis projects. Before coming to ARA, Andrew has a very long and varied career working with defence contracting companies in Australia and the US, the UK Met Office, and at the Anglo-Australian Observatory. And as he pointed out in his bio, that was looking up instead of looking down. So you've been doing it always, Andrew. Andrew is also a pilot and very actively involved in acquisition of the imagery and the data that he's going to be talking about. So Andrew, I'll now hand over to you for your presentation. Thank you.
Okay, thanks, Megan. And I hope my screen share is about to pop through to everybody. Yeah. Yeah. Okay, you should be able to see that now. Yeah, so thanks, Megan. So I'll be talking basically on exactly these topics that you've talked about. I had better highlight that Airborne Research Australia is the kind of unusual organisation. We're a not-for-profit independent research institute that we came out of Flinders University. We were originally part of the Flinders University, just a normal research group within the university. In 2016, I call it cast adrift, not spun off, because we're not for profit. We don't we don't make any money, and any money that comes in, it goes purely to supporting the organisation. And so we get funded by philanthropic donations and direct project money on research projects and so on. We're very firmly in the academic and research area, not big commercial stuff. What we do is environmental research from manned airborne platforms. And the group's been around for pushing 40 years now. And I highlight that registered as we are, these philanthropic donations are tax deductible. So that's an important thing for us to survive. So yeah, talking on the airborne versus spaceborne issues, that there are some really easy answers that that I mentioned partly in my icebreaker question there. You know, satellites give global or near global coverage, very standardized product that's revisited, on a very regular schedule. Cost is debatable. Depends on who's paying for it. Some satellite products are made freely available, but in general, the systems are expensive. Whereas airborne systems, because we're closer, we get better resolution and sensitivity. We have more flexibility as to the timing of data collection to fit around cloud or weather events, and it's much more customizable. We can put whatever instruments we want and set them up as we want for a particular project. And again, the cost is debatable as to how you cost these things, but in my experience, most of the costs of this sort of environmental sensing data is in the human time involved in processing and handling the data, often more than the data collection itself. And so I do see the satellite and airborne regimes as mutually supportive. And of course, different projects need different solutions, and you just got to choose what's best for the case. And so I know that a lot of people here will be coming to this webinar thinking purely along remote sensing, and Airborne Research Australia has a lot of experience in remote sensing. We're thinking stuff like photography, multispectral imaging, hyperspectral imaging in various wavelengths, thermal imagery, passive microwave, and then we go into active sensors like LiDAR and radar that I'm sure that people here are very, this audience is going to be very familiar with, and even others to sensing like gravity, which can be measured from an aeroplane for geological survey purposes. But something that an airborne sensor can do that satellites certainly can't do is in situ sensing. So we can, because we're in the air, we can measure it, what's there. We can do work on meteorology. We can do work on measuring pollutants and cloud physics and greenhouse gases. And I'll just mention right at this precise moment, Jorg Hacker, that many of you will know, is in one of ARA's aeroplanes flying around open pit coal mines, measuring methane emissions. That's in response to the recent methane sat and tropomi measurements that show very high levels of greenhouse gases leaking out of open pit coal mines. And when we're talking about airborne sensing, we have a huge range of scales that we can consider, from small, and these are the pictures I'm showing here are pictures of aeroplanes that Airborne Research Australia has worked with in the past. They're quite large aeroplanes, very specialised. When Megan mentioned that I worked for the UK Met Office, I was doing airborne remote sensing in this C-130, and that was again in direct support of satellite measurements. Our group built the AMSU-B atmospheric sounder for measuring temperature and humidity profiles through the atmosphere globally, and we also built an airborne copy of the same instrument so that we could support the satellite with measurements at different heights in the atmosphere underneath the satellite. What ARA has sort of settled on as what we think is a pretty ideal airborne platform to carry the instrumentation are these Echo Dimona aircraft, which we think are very special airplanes. Unlike all the other airplanes we've operated, these aircraft were designed on the drawing board as sensor platforms. They have a small environmental footprint themselves, being quiet, burning very little fuel. And the flight characteristics and the vibration characteristics of the aircraft are really optimized for high resolution sensing. Only 7 of these aircraft were ever built, and we've got 2 of them. That's what they look like. And we normally operate it with 2 people aboard. One person driving the aeroplane and one person driving the instruments. So the cockpit is divided in that way, with computer-y stuff on one side and aeroplane-y stuff on the other side. But under the wings is where we tend to carry most of our sensing instrumentation. And what you're looking at there is a large pod where we can put whatever instruments we like within reason, up to a 50 kilo payload in the big pod, and under the smaller outboard pylon, we can put 12 kilograms as well. So that this, even though the aeroplane is quite small, we have had it configured with over 120 kilograms of instrumentation all at one go. And a lot of what we do, and I'm going to move away from the remote sensing directly that I think a lot of people know about and talk about. I'll talk about some of our work with satellites in the past, or space-based instrumentation. Because we can use an airborne environmental sensing platform, not just to collect data for environmental projects, but also engineering support for space-based instruments. We can test fly the hardware itself, and Airborne Research Australia has test flown quite a lot of different airborne, different systems that are destined for space. And we can do calibration exercises for satellite instruments once they're up. And I say including right now at the bottom of this slide, because right at this, again, in fact, as soon as I get off of this webinar this afternoon, I'll be conducting a flight testing a navigation unit that was originally prototyped for a Mars lander by NASA, and is now part of a moon landing project under the Artemis program, and I'll be test flying the navigation unit, or the prototype of the navigation unit, for this moon lander this afternoon. And yeah, that's the NASA box mounted under the wing. So one of the things we think we're good at is taking other people's instruments and sticking them on the aeroplane. And in this case, that's a laser-based navigation unit that can work without GPS. And the flight characteristics of the aeroplane allow us to do some quite unusual sorts of flying that may be relevant to somebody landing on the moon. I won't go into it in detail, but the top trace shows the vertical component of the speed of the aircraft, which goes up to 45 meters per second. That's actually in a downward direction. So we're going 45 meters per second downwards, down to an altitude of under 200 meters. And not a lot of airplanes can do that. Yeah, I'm nearly finished here, because I'm going to just mention that this support and work coming out of satellite observations. So satellite observations can measure various pollutants and various effects on cloud. And what we can do with an airborne sensor is, for example, here we're looking at the fracking fields in the Surat Basin near Toowoomba. And with a methane sensor, we're able to fly a pattern around the whole gas fields and map the plumes of methane at really high resolution and super sensitivity. And by super sensitivity, this pattern is it's a map of our flight path colored by the methane concentration, and that's a group of cows in the middle. And so we're measuring the plume of methane being emitted from the cows. And my final point is on the resolution that's achievable from airborne platforms compared with space platforms. We've got a system that we've developed here at ARA that can do RGB imaging down to leaf scale, so centimeter scale images. And with accurate georeferencing, we get measurement of that. We've got a project that's looking at weeds just from the shape of the leaves, identifying weeds in crops. And my last slide is showing we can measure all sorts of things just by high resolution imaging. And the special thing about this camera system is that we're able to cover up to 10,000 hectares in a single day's flying at centimeter resolution. So I guess I'll finish up because we're running out of time, and move on to questions, or however Megan wants to handle it.
Thanks very much, Andrew. Some really interesting examples there of the quite distinctive and unique roles that you're playing using the Airborne platform, both to collect imaging data or different sorts of sensing, but also, as you say, in situ measurements, and some nice examples where you're linking with on-ground studies and satellite-based work as well. So I hope that we'll be able to pick up some of those things in a discussion at the end of the session. And I do note that in the chat, there's a comment that is particularly relevant to the calibration or validation capabilities somebody is interested in. So we'll now move on to Paul's presentation. Dr. Paul Dare is the founder and CEO of Fireflight Technologies, which is an Adelaide-based technology company that develops advanced airborne sensing and intelligence, surveillance and reconnaissance systems specifically designed for aerial fire mapping. Today, he's going to specifically talk about the Fireflight system and its unique capabilities, but I also would like to acknowledge and note that Paul is the founder and director of other airborne sensing companies, including Spatial Scientific. Paul's been working in remote sensing since 1994, and he too has had a very interesting and varied background that's highly relevant to what he's doing. He has been an academic at Australian universities. He's been a firefighter and a commercial pilot. So Paul, over to you for your presentation. Thank you.
Thank you, Megan, for that introduction. I'm just going to see if I can share my screen. Hit the share button. Okay, I will continue on the assumption that you can all see my screen. So yeah, thanks again, Megan, for inviting us along today. I really appreciate the opportunity to talk about some of the work we're doing. Andrew's just given us quite a broad presentation of a lot of different aspects of airborne remote sensing. I'm very familiar with ARA and the work they do, and got some excellent work there. I'm going to drill down and focus on one very narrow aspect, and that is bushfires. I'm going to be talking a lot about fires today. A little while back, I did a presentation and one of my kids saw it and they had a laugh. They said, "Hey, take a shot every time Dad says fire." So I'll try and drop the word fire a little bit. So Fireflight Technologies was a standalone company that was established in 2019. It's a spin-out company from the parent company, Spatial Scientific, which is basically an airborne technology sensor company that I established in 2005. And as Megan says, I've been working in the remote sensing industry going way back to 1994. So I've been doing this for quite a while. But Fireflight is really just a focus on the one very, very specific application. So just looking, if we go back a couple of years now to the Black Summer fires, 2019, 2020, some of the worst fires that Australia has ever seen. 18 million hectares of land was burnt. To put that number in some sort of perspective, 18 million hectares, that's the size of England and Scotland, or the size of Cambodia. You know, we're talking a huge area of land. 2 billion animals were killed. Some species were pushed to the brink of extinction. Tragically, 34 lives were lost as a direct result of the fires, and it's estimated another 400 to 500 lives were lost due to the secondary impact of fires. We can count ourselves as lucky that we haven't had such a bad season since then, but we know with global heating that we are going to see more black summers. The fire is just getting worse and worse every year. Not just in Australia, but globally. And we're seeing fires in other areas of the world where you'd never expect to find fires. Our focus is on understanding and helping firefighters to work with, work in the fire more safely. This image here shows a typical bushfire on the ground. Very often when you're fighting a fire, it can be dark, it can be smoky. There's fire all around, there's sunlight. You don't know where you are, you don't know where the fire is, you don't know which way the fire is moving. It's basically a chaotic situation. It's like a warlike situation, it's like a battlefield. And what we're trying to do is give the firefighters better tools to fight the fire. like on any battlefield, you need ammunition, you need intelligence, and we're trying to provide the intelligence aspect of that. Looking at the fire from the air, it's still pretty chaotic down below. So when a fire occurs, you have spotters in helicopters that fly around. They make visual observations of the fire and they radio those observations down to the ground. What we're doing is working on mapping fires, making an accurate geospatial map that we can share with everyone in real time, so people can plan their actions, so the general public can work out a way to escape, or firefighters can work out where to best deploy their resources. So this is a sensor system that we've built here in Adelaide. We've built this from the ground up. The hardware comprises 2 thermal imaging sensors. One's got a very narrow field of view, one's got a wide field of view. It's got inbuilt GPS and inertial measurement units. So the GPS for giving us an accurate position of where the sensor is, and the inertial measurement unit for defining which way the sensor's pointing. This is combined with a Windows PC in the aircraft, and screens for the pilot and for the operator. So similar to what Andrew was talking about, we also run a 2-crew system in the plane, a pilot flying the plane, operator operating the system and talking to people on the ground. The system also comprises some software as well, pilot navigation, camera control, and importantly, real-time processing. This shows an example of the processing chain. So the line of images at the top there, they're the images that come in with the come into the camera. The first thing we do is we colorize the images to separate fire from non-fire. Then using the GPS and the attitude data, we apply direct georeferencing, which is basically converting the image coordinates to lat longs to ground coordinates. We then mosaic those images and then we upload them to a web server. We do this in an aircraft in real time on the PC there. So this, when we talk about real-time data, we're talking about data that we're creating literally within seconds of acquisition. And that is super important to the firefighters. You know, there's less and less value in this sort of data the longer it is between acquisition and delivery. So we've perfected a system now where within sort of 30 seconds of flying over the fire, we can have this data available to anyone on the ground. And then 5 minutes later, we replace the image with a new one, an updated one. And then 5 minutes later, another updated one. And we can sit over a fire for 7 or 8 hours and just continually upload this data. So the fire agencies have maps which are changing in real time, and they can then see the progression of the fire and where the resources need to be deployed. This shows an example of just one of the strips we flew over a fire, and you can see here it's projected onto Google Earth, but we also have a web browser option where this can be pulled up on your personal electronic device, and you can see this this imagery in your web browser, no matter where you are in the world. The quality of the, let's say the accuracy of the geometric alignment is pretty good. With the technology we use, we can get the accuracy down to the sort of the 5 to 10 meter range, and the pixel size or the resolution of the imagery is somewhere between 2 to 5 meters. We've experimented with much higher resolution data, and we found out get a lot more data, but we're not getting any more information. And in fact, coarser resolution data is just as good to firefighters. This means that we can fly very high over the fire. We don't need to fire close to the ground. So we'll be operating about 10,000 feet or about 3,000 meters over the fire. And in that way, we stay away from all of the other aerial firefighting traffic. So associated with any fire, there's lots of other traffic. There's helicopters, there's water bombers, there's the large air tankers. They all operate way, way below us, and we sit right above, out of the way of that traffic, and also out of the smoke plume. So we're sitting in the nice cool air, looking down from our very calm God's eye view of the world, and creating this imagery in a very sort of stable environment. So this is the platform we use. This particular one is Piper Comanche. It's a single engine 4-seater aircraft. It's got a good bit of speed to it and a good bit of endurance, but we can basically put our system on really any manned aircraft platform or even a helicopter. It doesn't really matter. When it comes to aircraft, we're very much platform agnostic. We can strap them to a Cessna or a Piper, whatever. What's important is as long as we can get the platform in the right place, which is overhead the fire safely, away from the smoke column and nice and high. This is our view of the world when we're up there. We get as I say, a nice wide area view of the fire. So I'll just take you through some typical results that we can generate. This is a screen grab from some image data that we collected over the Kangaroo Island fires on the 9th of Jan in 2020, which was Black Summer. This was when the KI was at its peak. Excuse me. And you can see we've got Vivon Bay down the bottom center of the image. And just to the north, you can see there's some fire burning down through some native veg between some open cropping areas. This was taken at 2 o'clock in the afternoon. You can't see it from this image, but I can tell you that the wind was blowing strongly from the northwest. And both of these fire areas you can see in this image were seen as being a very high threat. And the firefighters were working very hard to get those under control. We just go to 3 hours later, so 5 o'clock in the evening. We were still up there collecting data, and you can see now that those fires that were burning up in the native veg have carried on down through the native veg, jumped the road, jumped the airstrip at Vivon Bay, and got into this whole area just out to the east of Vivon Bay, burning through all the native veg. The firefighters weren't so concerned about the eastern side of the fire because that wasn't going to impact any infrastructure. But down on the western side, you've got the Vivon Bay township, and the firefighters were working very hard to get this boundary under control down the western side. So what this data can tell us is initially, obviously exactly where the fire is, gives an indication of the intensity of the fire as well. But also you've got some other information you can derive from this. You can see the main road coming down the island. And you can see at this point, there's fire on both sides of the road. So that road is pretty much inaccessible. No one's getting through there. You're not putting a fire truck through there. And obviously the airstrip is inaccessible as well.
Paul, just a couple of minutes, thanks.
And this is a sort of view we get from the aircraft. This is about 10,000 feet, a small fire. This is actually a controlled burn over in the Narcat Conservation Park. But this smoke plume's got up to 10,000 feet. We're staying well away from it, but we can penetrate through this smoke, and we can clearly see the fire down on the ground there, and we can see how the fire moves as well. So just to summarize some of the stuff I've sort of spoken about really quickly here, firefighters need real-time geospatial intelligence, and we're trying to develop exactly the right technology to fill that gap. Remote sensing provides the information that people need, and this can't be done with satellites. We can't get the loiter capability, we can't get the resolution, and we can't engineer the sensor on the satellites to be exactly what we need for fires. So really, manned airborne remote sensing is the only way to do this. There's actually a lot of interest in unmanned applications, but at this stage and for at least the next 5 to 10 years, we're not putting unmanned aircraft up around fires. It's too dangerous for the other firefighting traffic. So just to reiterate a point that I made earlier on, space is cool. It gets a lot of the national focus, and why not? Hey, we all love space. But we mustn't forget that for very specific applications, these other technologies are much more appropriate. So I'll leave it there. Thanks.
Thanks very much, Paul. And after that presentation, I think the audience would have to agree that airborne sensing and what you presented is very cool too. A very impressive capability, bringing together specialist sensing, processing on the fly, and delivery to be able to give people information in real time in such a challenging situation. And I can see some questions coming up, certainly specifically about your technology, but encourage people to post those questions, and we'll draw on those for a question and answer session towards the end. Thanks very much, Paul. So now we'll move on to Daniel Krumel, who will give our third presentation. Daniel heads AAM's sales team in delivering advanced geospatial solutions in the Asia Pacific region. After 2 years working prior to that for a LiDAR manufacturer. His background, and he started as a land surveyor, but he's had exposure to a very wide range of spatial disciplines, both on the consulting side and on the supplying side. So Daniel, over to you for your presentation. Thank you.
Thank you. I'll just quickly do the share screen formalities. Thank you very much for the invitation today. And look, my presentation is going to be a little bit shorter than the preceding ones, which have been really good from Paul and Andrew. But excuse the pun, mine's just going to be a little bit more high level from a commercial airborne sensor operator, just some of the predictions and trends that we're seeing in the market. So just quickly, for those of you that don't know about AAM, a company that originated in Australia. It actually started in 1959 and was Australian aerial mapping, hence AAM. We do a little bit more than just that now across all of the geospatial disciplines, but aerial mapping is still at the core of our business. We've got over 42 countries that we've worked in, several thousand projects that we do, and then every year over 300,000 square kilometres of aerial mapping. But I won't harp on too much more of that, but that just sort of gives you a background of where I'm coming from. So look, I just really wanted to, I guess, pose a few thoughts and ideas, and just what I've really seen, the industry, develop over the last few years, and where I think it might go, or some of the key developments that's going to come in the years ahead of us. So on processing, actually Paul's point there was really interesting on the need for real-time information from a firefighting perspective, and absolutely that's a use case where the information, the longer it goes from when you've captured it, the less valuable it is. But we're even seeing for a lot of our commercial clients, time is money now. So where they would have usually taken 2 to 3 days to get the data from when we've captured it, we're being pressed to do that much quicker, particularly from a lot of mining and resource clients. So from processing, we've in response to this developed a automated processing pipeline in AWS. And the idea behind that was we were asked to do 12-hour turnaround from when the data was actually captured. And the only way that we could possibly do that was by using automation and using cloud processing for scalability. And I think I would sort of see one of my predictions in the next few years, we're going to start to see real-time, LiDAR and imagery processing, on the platform as it's being captured, to just even further bring that turnaround time, down from 12 hours to basically instantaneous. Something else, just new sensors coming onto the market as well. Now, AAM recently became a part of Woolpit. So Woolpit is a very large global architecture, engineering and geospatial firm. And Woolpit were proposed a challenge a few years ago by a group called the Joint Airborne LiDAR Bathymetry Technical Center for Excellence, or JABLTEX, which is a division of the United States Army Corps of Engineers. And for those of you who aren't familiar with bathymetric LiDAR, it's a great technology for capturing LiDAR in the coastal zone, where it's very inefficient to do it with traditional vessels with sonars equipped. And I know satellite-derived bathymetry has been a huge advancement for hydrography as well, or for bathymetric surveying. And we've seen a lot of use cases where that's been able to provide data in cases where it hasn't been able to be easily acquired before. But certainly from an accuracy perspective, still using laser or sonar, can be a little bit more suitable for then producing nautical charts. So Woolpit was proposed a challenge to develop a sensor that could be much more efficient and could map at more tactical altitudes, so around 3,000 meters AGL rather than 400 meters AGL. And that sensor is still in its final stages of R&D, but the prototype has shown some really promising results from being able to achieve that challenge of the same point densities and accuracies. More vertical accuracy, horizontal accuracy does increase a little bit as you, or I should say, the errors increase a little bit as you increase that flying height to 3,000 meters. But it's been very, very promising so far. And then the other advantage just being that you can cover a much wider area, so it's going to be more efficient. I think the other thing that I'll just mention on new sensors and technology, Paul mentioned it before about manned aircraft, being needed for firefighters. I would, or for that fire mapping. Look, I won't put a number on when it's going to happen, but eventually we are going to see large unmanned systems flying around doing what we're currently doing in manned aircraft now. There's some technological advancements that need to come before that happens, and there's also some regulatory requirements. I'm not sure whether it's 5 years, 10 years. I wouldn't be brave enough to stake my life on a number, but I'm not crazy enough to think that throughout the course of the rest of my career that it's not going to happen. So that is going to come one day. And that kind of leads into the next one, which is value as well. And I mentioned a few brief things on this, just in terms of what we see if someone's looking at, particularly around that 50 centimeter spot that satellite is starting to get down to. I know probably a lot of this community is more on the researchy sort of side of things, but I guess from a commercial aspect, the satellite providers see that 30 to 50 centimeter high resolution product has been much more expensive because that's their premier top tier product. We're finding that we can still go out and capture 50 centimeter imagery with an aerial platform, at least depending on the scale that well, actually at 50 centimeters we probably can compete, but it's still cheaper for us to do that in a manned aircraft than it is to do it sourcing via satellite or tasking. But as I sort of said, really it comes down to a cost benefit analysis. If you're looking at a whole state and resolution of 1 meter or above, satellite is definitely going to be the answer, and it's going to provide the best value turnaround. As you start to change the scale that you're looking for, particularly RPAS technology, we're certainly seeing if you're on a small area, RPAS is going to give you a much higher resolution and a much better prospect and value for what you're tasking. But really, I just see this all as part of an ecosystem of different platforms, different solutions, and they've all got a place in the market. I'll probably leave it at there just to make sure that there's enough time for questions.
Thanks very much, Daniel, for your presentation. High level, pun appropriate, but also appreciate that you've talked about the future directions and where things are going and the distinctive niche that airborne sensing can have, as you say, in that broader ecosystem. Thank you very much. A number of questions have been coming into the chat, and some are fairly specific and technical, addressed to particular speakers, and I can see that some of the speakers have been responding to those, so I'm not sure that we'll be able to cover all of those. questions about particular types of sensing, hyperspectral, what extent is it being taken up by industry? Sadly, not enough, Andrew says. If I come back to an early comment, just looking here, an early comment from Kotska Wallace, who works with, or who's optical payload manager for EarthCare mission at European Space Agency. Kotska is interested in the validation capabilities in Australia with some fairly specialised sorts of sensing. And some of those certainly have been mentioned in our presentations today. Andrew, for example, some of these forms of sensing are ones that you deal with, and you talked about the calibration or role of some of your work. Do you want to add to that comment?
Sorry, I'm actually still trying to find the actual comment. This is Kotska's
yes.
comment.
Yeah. Kotska's interested in the validation capabilities in Australia in cloud radar, high spectral resolution LiDAR, multispectral imaging, and broadband radiometer, particularly airborne, to validate space missions.
Yeah, well, in some ways, Australia is actually a pretty good place to do some of this sort of satellite validation, because we tend to have fairly large areas of homogeneous surfaces can be that work well for exactly that purpose. You know, we have big salt lakes, we have areas of sand, we have areas of relatively homogeneous vegetation and exposed soils and rocks. And so for that reason, Australia is potentially useful in this area. But in terms of the actual sensors they're talking about, I mean, those sorts of sensors, like, you know, the high resolution LiDAR, it's really a matter of wherever the LiDARs are. I'm not familiar, I've never worked with high spectral resolution LiDAR. I mean, we can do, I think most of the people who work in this field now have access to very high spatial resolution LiDARs, which are probably less useful for satellite calibration, because we're looking down at individual deer tracks or individual branches on a tree that are not necessarily useful for calibrating the satellite. But yeah, there are certainly capabilities here in Australia to fly pretty much any sensor that can be brought here.
Thanks very much, Andrew. Daniel, you've posted a question, and Paul might like to respond. Daniel, you touched on some of the regulatory issues for aircraft and for unmanned vehicles that we're seeing more and more of. And Paul, do you have any issues with STC for your various platforms that you use?
Yeah, so just for the rest of the audience, STC stands for Supplementary Type Certificate. It's a piece of paper that says whether you're allowed to modify an aircraft in a particular way to put a sensor on there. Obviously, safety's got to be at the forefront of all our airborne operations, and we can't just go bolting things to aircraft willy-nilly. We have to do things properly. So yeah, in answer to Daniel's question, no, we work with maintenance engineers, and we're generally able to get our equipment onto aircraft pretty easily. The equipment we use is very small and lightweight, just a couple of kilos. Any aircraft with a camera hatch, we can just get on there generally without a problem. And if the aircraft doesn't have a camera hatch, it's pretty easy to cut a hole in the plane these days. You know, a sort of a Cessna or a Piper type aircraft, the sort to see at your local flying club. And we've designed our equipment specifically for that reason, that we can use these small aircraft which are widely available, because we'd like to see our sensors operating all across the country, and we can't afford to put specialized aircraft all around the country. We have to use what's out there, what's available. So if we can get access to all these aircraft sitting around the airfields then that means we've just got more opportunity for getting our sensors in the air in the fire danger regions, and that's not just Australia, but fire danger regions worldwide. So so no, it's STC of the equipment. Yeah, it was a big question early on, but we've managed to work around that.
Thanks very much, Paul. I'm seeing some more fairly specific questions in the chat, but I'm afraid, given the time, I'm not sure that we can have a discussion about those. But Andrew and Paul, you might want to respond to those. Particular sorts of sensing, subsurface rocks, and so on. I think in the examples that all of you have presented, you've shown the versatility of the Airborne platform, and that there's scope for mounting all sorts of sensors for all sorts of applications. So, but I'll perhaps ask you if you could respond to that question. Given the time, I think we'll now move to wind up the webinar. And Larissa, you might be able to share the slides. So I'd like to thank you to our three panelists. Thank you very much for your presentations, all of the trouble that you've taken to address the questions that we posed and to think about the broader context of where airborne sensing fits within the Earth observation ecosystem or landscape. So thank you, Andrew, thank you, Paul, and thank you, Daniel, for your presentations.
Thank you, Megan.
I'd like to thank Larissa Marfan, the Earth Observation Partnerships Coordinator, who's been manning the chat and making sure that all of this runs smoothly, and who was behind the scenes preparing all of this, supported by the Earth Observation Australia office, and the directors of the Advancing Earth Observation Forum for the concept and the initiation of the webinars. So I hope this has stimulated your interest and raised questions. Clearly there are lots. I'd like to encourage you to attend the forum in Brisbane in August. Registrations are now open. There's an exciting program. There will be an opportunity to meet face to face and ask these questions, discuss ideas, and so on. So certainly look forward to seeing you there. But I'd also like to point out that Earth Observation Australia this year has launched some awards, 3 awards for people or groups or organisations involved in Earth observation. The details are on our webpage. Applications are open now, and the awards will be announced at that forum. So I'd encourage you to have a look at that as well. Larissa has posted a link. We'd really appreciate your feedback on this particular webinar, but on the idea of these webinars generally. And there's one more webinar in this series before the forum, so please keep an eye on our webpage and your inbox for news about it. Thank you, everybody. Thank you again to our speakers, and thank you for the interest from our audience today. I'll close the webinar now. Thanks very much.
Thank you.
Thanks, Megan.